Hi, this is Dr. Habib Ahmed. Welcome to my MATLAB tutorial. Today I will demonstrate a powerful simulation tool that calculates the full width at half maximum and the fractional full width of the maximum peak, which are key metrics in signal processing and scientific analysis. We will explore their significance in symmetric and asymmetric rocking curve measurements in X-ray diffraction and also in photoluminescence measurements. Full width at half maximum is crucial in order to determine the quality of crystal structures, providing insights into strain, defect densities, and overall material properties. So here I mentioned that I'm going to demonstrate the calculation of full width at half maximum and also fractional full widths of the maximum peak, which means that I will demonstrate the calculation of the 1/10th of the maximum peak, then full width at 1/100 of the maximum peak, then full width at 1/1000 of the maximum peak, then full width at 1/10,000 of the maximum peak. There is only one condition. I have set the noise level at an intensity count of 10. So if the intensity count for any of these is above 10, then the program is going to calculate the value for me. Otherwise, if it is below 10, then the program assumes that this value is below the noise level and it's not going to give a full width value for that particular parameter, I would say. So now the question is, a lot of you might know the requirement for full width at half maximum. But now the question is, why do we need to calculate the fractional full widths of the maximum peak? So it depends on the scenario. In some scenarios, we may need to determine the fractional full width of the maximum peak, and in other scenarios, we might not need to calculate the full widths of the fractional full widths of the maximum peak. And let me give you an example of both. So in the first example, I deposited aluminum on top of, as you can see, A-plane sapphire, and I deposited aluminum on another sample which was on top of C-plane annealed sapphire. And you can see the results over here. For the C-plane sapphire, my full width at half maximum is 820 arc seconds. However, for aluminum deposited on the A-plane annealed sapphire, my full width at half maximum is 144 arc seconds. So you clearly see the crystal quality difference between the two films. The aluminum film deposited on A-plane annealed sapphire gives much better crystal quality as compared to aluminum deposited on annealed C-plane sapphire in this case for this comparative study. So here you don't need to calculate the fractional full widths of the maximum peak. However, there could be other scenarios. For example, let me talk about two samples. In fact, let me talk about the next two samples. So I performed a comparative study where I grew gallium nitride films using metal modulated epitaxy, which is an advanced version of molecular beam epitaxy. So I grew the gallium nitride films in the temperature range of 500 to 750 degrees C. But here I'm just going to talk about two samples. One film grown at a substrate temperature of 500 degrees C, and another gallium nitride film grown at a substrate temperature of 650 degrees C. So the film grown at a substrate temperature of 500 degrees C gives me a full width at half maximum value of 79 arc seconds, while the film grown at a substrate temperature of 650 degrees C gives me an FWHM value of 101 arc seconds. So you may think, since the FWHM value of the film grown at 500 degrees C is better as compared to the FWHM value of the film grown at 650 degrees C. So you might think that this film, which is grown at 500 degrees C, has a much better crystal quality as compared to the film grown at 650 degrees C. But it's not the case. And let me prove it with some other studies. So it was actually a really comprehensive study in which I did not just perform X-ray diffraction measurements, I also performed atomic force microscopy measurements, Hall effect measurements, then photoluminescence measurements of the samples, and along with X-ray diffraction measurements, we also performed transmission electron microscopy measurements of a lot of samples, and we published a paper based on this and its comprehensive analysis of metal modulated epitaxial gallium nitride films. I'm the first author in this paper, and my advisor is the amazing William Allen Doolittle. So in this paper I performed like a lot of studies, but let us just focus on the substrate temperature part. And I'm gonna show you a comparison of the films grown at 500 degrees C and at 650 degrees C. So here is an atomic force microscopy image of the film grown at 500 degrees C, and then here is an atomic force microscopy image of the film grown at 650 degrees C. The RMS roughness for this film is 1.5 nanometers, while the RMS roughness for the film grown at 650 degrees C is sub-nanometer. It's 0.60 nanometers. Also, this film demonstrates step flow surface morphology. So from AFM, the 650 degrees C film clearly gives better quality. Then I also performed Hall effect measurement, but let's focus, I would say, on the transmission electron microscopy measurement. So here is 002 and -100 transmission electron microscopy measurement of the films grown at 500 degrees C and at 650 degrees C. This thin film over here represents the metal modulated epitaxy grown gallium nitride film. It has a thickness of 500 nanometers. From here you clearly see screw plus mixed threading dislocations and edge plus mixed threading dislocations for the film grown at a substrate temperature of 500 degrees C. However, the film grown at a substrate temperature of 650 degrees C demonstrates excellent crystalline quality, not introducing any extra screw or mixed threading dislocations except the ones which are already originated from the substrate. So from this study, now we know that the film grown at a substrate temperature of 650 degrees C gives us much better crystal quality as compared to the film grown at a substrate temperature of 500 degrees C, which also means that in this kind of scenario, measuring full width at half maximum using XRD would not be enough. And then I also performed like photoluminescence measurements of these samples, where you can see the results for the photoluminescence measurements. So we also see like the full width half maximum in terms of milli-electron volts for 500 degrees C and 650 degrees C. So it means that measuring just full width at half maximum in some scenarios might not be enough. So then if you go back to these two samples, we may see that although the film grown at 500 degrees C gives relatively better full width at half maximum, in fact it's comparable. There could be slight measurement error as well. 79 degrees here, 79 arc seconds or 100 arc second actually corresponds to really good crystal quality. So however, if you focus on the base of these rocking curve measurements for XRD, you see broadening of the rocking curve for the sample grown at 500 degrees C in the base of the measurement. And now if you look at the sample grown at 650 degrees C, you don't really see that much broadening. So if you compare full width at 1 over 1000 or 1 over 10,000 of the maximum peak, if for example focus on 1 over 1000 of the maximum peak, you see a full width at half maximum of 993 arc seconds as compared to 2648 arc seconds for the film grown at 500 degrees C, which means that clearly the film grown at 650 degrees C demonstrates better crystalline quality. And I'm also going to show you the results overlaid on top of each other. So here the green curve represents the rocking curve, symmetric rocking curve measurement for the gallium nitride template. The red curve corresponds to the metal modulated epitaxy grown film at a substrate temperature of 650 degrees C, which is super close to the crystalline quality of the substrate. Now look at the blue curve, which corresponds to the film grown at a substrate temperature of 500 degrees C. Now you clearly see broadening of this measurement, broadening of the rocking curve measurement in the base of the measurement. So from comparing the base or the fractional full widths of the maximum peak, now you clearly know that the film grown at a substrate temperature of 650 degrees C has a much better crystalline quality as compared to that of the one grown at a substrate temperature of 500 degrees C. And our group, like my PhD advisor, Dr. William Allen Doolittle, he named the fractional full widths of the maximum peak per leaf XRD measurement. So this is a special terminology which is introduced by Dr. William Allen Doolittle, and he reserves the rights to this. So if you're going to use them, you have to give credit to Dr. William Allen Doolittle. Now I also talked about the aluminum films grown on top of A-plane sapphire and C-plane sapphire, and for this you clearly see like broadening in the film grown on C-plane sapphire. So even the full width at half maximum measurement gives you a comparative study of the crystal quality of these two aluminum films grown on A-plane sapphire and C-plane sapphire. So in this case you might not need the fractional full widths, but in other scenarios you definitely need the fractional full widths of the maximum peak, which we now call per leaf XRD measurements. Now let us focus on the MATLAB code, which gives us the full width at half maximum and fractional full width at half maximum. So whether you are analyzing XRD measurements, photoluminescence or other techniques, this program automates the entire process from data import to analysis and visualization. Let's get started and streamline your data analysis. So for this purpose, I got two MATLAB script files for you. And by the way, I also want to give credit to my colleague, Dr. Evan Andrew Clinton, It was actually primarily he was the person who initiated this code and shared it with us. So for this purpose, I got two MATLAB script files. The first script is importfileRC, and it's a utility function for data import. So we use this file for importing our script, our data files. Then the second script, which is FWHM underscore XRD underscore RC underscore scan, is the main analytical tool. Together, these two scripts automate the process of importing, processing, and analyzing, and also visualizing data to calculate the full width at half maximum and fractional full widths of the maximum peak in a data set, which is a common task in signal processing and other scientific analysis. So now let me discuss these two script files. Let's talk about the first one, importfileRC. This MATLAB function importfileRC is designed to read a CSV file to extract two specific columns of data. Since we are talking about XRD initially, so the two columns would be omega, corresponding to the angle, and counts, which correspond to the intensity counts, and return them as output variables. The function allows the user to specify the starting and ending rows to read. Now let us discuss this code block by block. For example, this first block over here defines the main function importfileRC that will read and process data from a CSV file, comma separated values file. The function takes in a file name and optional row range parameters start row, end row. It returns two variables, omega and counts, which represent the data extracted from the file. This block over here sets up the delimiter used to separate the data within the file. Since it's a CSV file, the delimiter is a comma. This tells MATLAB how to distinguish between different data fields when reading the file. This block ensures that if the user does not provide start row and end row arguments, the function assigns default values. The function will start reading from row number 26 and will continue until the end of the file if these arguments are not specified. This is useful for handling files with consistent formats where the data always starts at a known row. So why a starting value of 26? So let me show you an Excel file for example, for the gallium nitride film grown at a substrate temperature of 650 degrees C. Here is the symmetric rocking curve measurements, and as you can see over here that the measurements start at a row number 26. So that's why I've given a value of 26 in the script over here. Now let's talk about the next block. This block defines how the data in the field should be read. It tells the function to expect two floating point numbers in each row and to ignore certain columns. This is crucial for correctly parsing the file, especially when not all columns are relevant to the analysis. This block opens the specified file for reading. By doing this, the function gains access to the file's contents. It is prepared to start processing the data. The file remains open until the function explicitly closes it. Now let's talk about this one. This block reads the data from the file based on the format specification, starting from start row and ending at end row. The function skips any header lines and reads only the specified data range. This block is the core of the function, as it captures the required data from the file into a MATLAB array, which is data array. This block handles cases where the user specifies multiple row ranges. If there are multiple blocks of rows to be read, this loop iteratively processes each block. It repositions the file pointer to the start and reads each block of data, appending it to the existing data in data array. This ensures that all relevant data across different row ranges is captured. This block closes the file after the data has been read. Closing the file is important for freeing up system resources and ensuring that no data is left unwritten or unprocessed. It is a good practice in file handling to close files once operations are complete. The final block extracts the relevant columns from data array and assigns them to the output variable omega and counts. These outputs contain the data that was originally stored in the first two columns of the file. The function then returns these variables to the user for further analysis. So overall, the function importfileRC is designed to read specific data from a comma-separated value file, starting and ending at specific rows. It handles missing input arguments, processes multiple blocks of data if necessary, and returns two key columns of data. This function is useful for efficiently importing and structuring data from files for further analysis. Now let's talk about the next script file, which is this one. FWHM_XRD_RC_scan. This script is designed to calculate and visualize the FWHM of peaks in a data set extracted from a CSV file. It allows for smoothing of the data, comparison of the peak width at various fractions of the peak value, and handles noise by setting a threshold, which I already discussed that in this case we are setting a threshold of 10. And then the results are displayed in the MATLAB command window and visualized on a plot. Now let us talk about this script block by block. This block clears the MATLAB workspace, removing all variables, functions, and data. This ensures that any previous data or variables do not interfere with the current script's execution, providing a clean slate for the operations that follow. Now this is a crucial block. This block sets up key parameters for the script. Decades defines a set of fractional values to calculate different levels of the full width of the maximum peak. Noise floor is a threshold value for distinguishing significant signal levels from noise. So I've set a noise floor of 10, which means that any intensity count which is below 10 is going to be considered noise, and the full width for that would not be calculated. Times to smooth specifies how many times the data should be smooth to reduce noise. Start row and end row define the range of rows from the data file that will be processed. The default is to start at row number 26 and continue to the end of the file. Why row number 26? I already demonstrated there. This block handles file selection and data import. A file selection dialog allows the user to choose a CSV file in this case. So here is .csv, but you can also change this to like .txt to open a text file. I've saved the XRD results in Excel sheets, so the .csv command is going to work for the XRD measurements, but I've saved the photoluminescence measurements in text files. So in order to perform these measurements for the photoluminescence, I have to change this command to .txt. The selected file's path is combined with its name to get the full file path. Data from the selected file is imported using the importfileRC function, which returns the data as omega and counts. And then any zero values in counts are replaced with NaN to avoid skewing the analysis. Zeros might indicate missing or irrelevant data. Now let's talk about smoothing the data. So this block smooths the counts data using a moving average filter. The smoothing is applied times to smooth times to progressively reduce noise. So I already introduced this variable times to smooth somewhere over here. Here times to smooth is 5. So this for loop is going to run 5 times for smoothing of the data. A convolution operation is used to apply the smoothing kernel, which averages the data within a window size of 3 over here. The same argument ensures the output is the same length as the input, preserving the original data size. So I used a moving average filter over here, but instead of that you can use smooth command over here. I have not used a smooth command because I have not installed the signal processing tool in my MATLAB. But if you have installed the signal processing tool in your MATLAB, you can also use counts is equal to smooth of counts, and that is going to work even better for you. This block performs initial calculations for peak detection. Data points stores the number of data points in counts. Step size calculates the difference in omega values per data point, representing the resolution of the data. Max counts and max index identify the maximum value in counts and its corresponding index, marking the peak of the data. Halfway is to set to the index of this peak, dividing the data into 2 parts for subsequent analysis. This block sets up variables needed for full width at half maximum calculations. Above noise is set to noise floor to determine the minimum intensity level considered above noise. Search for calculates the target intensities at various fractions of the peak value, which is maximum counts. Searches counts how many different target intensity levels are being calculated based on decades. This block identifies the points corresponding to the full width at half maximum. Search array and subtract array are created by replicating the counts data and search for values respectively to allow for element-wise operations. Min array calculates the absolute difference between counts and the target intensities which is searched for, helping to find the closest matching points. I1 and I2 are the indices of the closest matches to search for in the first and second halves of the data, corresponding to the lower and upper full width half maximum points along the x-axis, which is the omega axis in case of XRD measurements and energy in case of photoluminescence measurements. O1 and O2 store the omega values at these indices. This block calculates the full width at half maximum. Full width at half maximum is determined by multiplying the step size by the difference in indices between I2 and I1. The full width at half maximum is then converted from degrees to arc seconds. We know that 1 degree is equal to 3600 arc seconds, providing a more precise measurement for comparison purpose. This block outputs the calculated full width at half maximum values. Depending on whether the calculated full width at half maximum is above the noise floor, the script prints either the full width at half maximum value or a message indicating that the full width at half maximum is below the noise floor. The results are displayed in both degrees and arc seconds for each fractional peak. This block provides a completion message to the user, indicating that the full width at half maximum calculation process is finished for the selected file. This block prepares the data points corresponding to the full width at half maximum for plotting. FWHMX stores the omega values at the FWHM points. FWHMY stores the corresponding counts values. These will be used to visually indicate the full width at half maximum on the plot. This block creates a plot of the data. The script sets up the figure window's position and size based on the screen resolution. It uses a semi-logarithmic plot, semi-log y, to display counts versus omega. The FWHM points are overlaid on the plot with a thicker line highlighting where the FWHM occurs. Titles and labels are added to make the plot informative. Then this semi-log command over here plots the FWHM points on the same figure. Title, X label, Y label, add a title, and these commands add a title and X label and Y label to the plot. Okay, so I'm trying to make my mouse work now. Okay, cool, it started working now. Then finally this block annotates the FWHM points on the plot. Shift O determines the horizontal offset for text labels. For each calculated FWHM, the script adds text annotations indicating the arc second. So this completes the explanation of the code. The script primarily imports data, smooths it, finds the FWHM values at different levels, and also the fractional full widths of the maximum peak, and plots the results with appropriate labels and units. So now let me demonstrate how the code is going to work. For example, for XRD measurements, I'm going to enter .csv over here, and let me go to this figure. So let me first show you the results for aluminum deposited on A-plane annealed sapphire. So I run the command, I run the program, and then I have to find the path for this sample. So this is aluminum deposited on A-plane sapphire, and here is the file for the symmetric rocking curve measurements. So I open that file. We can also look at the runtime window over here, and you can see the FWHM value in degrees and arc seconds, then full width at 1/10 of the maximum peak, and degrees and arc seconds, then 1/100 of the maximum peak, 1/1000 of the maximum peak. It also tells us that the full width at 1/1000 of the maximum peak is below the noise floor. Similarly, the full width at 1/10,000 is below the noise floor. So we can check the status in the runtime window, and we can also see the results over here. Full screen them, so we can see the results over here as well. You can see the full width at half maximum is 144 arc seconds. Similarly, we can see the full width at 1/10 of the maximum peak, which is 468 arc seconds. Then the full width at 1/100 of the maximum peak, 1252 arc seconds. The full width at 1/1000 and 1/10,000 is below the noise level. Our noise level, we have set it to 10, an intensity count of 10. So any value below that would be considered as noise. Now let us zoom in on the peak over here. Here is the peak, and let us determine the peak point, which is 19.28. So we are talking about omega axis. So in terms of 2 theta, it corresponds to approximately 38.5 degrees, which corresponds to aluminum film. So similarly, we can zoom out once again. Delete that data point, and we can play around with the figure properties. For example, we can set the font to bold. Similarly, we can increase the line width of this line as well to, I would say, 2 degrees. And similarly, so this is the symmetric rocking curve measurements for aluminum deposited on A-plane sapphire. Let me quickly show you some results for C-plane sapphire as well. As you can see that this one has a broader full width at half maximum, which means that aluminum deposited on the A-plane sapphire gives better crystal quality. Similarly, I want to show you the symmetric rocking curve measurements for the gallium nitride template, which we got from MACS. It is an iron doped semi-insulating gallium nitride template. So you see the symmetric rocking curve measurements for the template. Similarly, let me show you the symmetric rocking curve measurements for the sample grown at a substrate temperature of 500 degrees C. Here are the results, and you see that the base of this symmetric rocking curve has broadened. So the base over here is going to give a fair comparison with the rest of the samples. And why do we see a sharp peak over here? Because it's actually deposited on a semi-insulating gallium nitride template. It's a thin molecular beam epitaxy grown film deposited on top of the substrate. So a majority of the intensity counts over here are going to come from the substrate and not from the deposited thin film. Now let me show you the symmetric rocking curve measurements for the sample grown at a substrate temperature of 650 degrees C. Cool. So here are the results, and I also compiled them over here in these slides. So XRD of aluminum deposited on A plane annealed sapphire, aluminum deposited on C plane annealed sapphire, then XRD of the gallium nitride template, XRD of the film grown at a substrate temperature of 500 degrees C, XRD of the film grown at a substrate temperature of 650 degrees C. And these are the photoluminescence results of the gallium nitride template. We can also perform the measurements on other samples as well. But just for demonstration purpose, you can see now that the x-axis is in it is the independent variable is energy now. In previous cases, in case of XRD, it was omega for symmetric rocking curves, but now for photoluminescence measurements, it's energy in electron volts. And similarly, the full width at half maximum is in milli electron volts. The fractional full widths of the maximum peak or the per leaf measurements are also in milli electron volts now. The y-axis or the dependent variable has a unit of arbitrary units. It is intensity counts. So let me show you how to set it up for photoluminescence measurements now, and then you can play around with the code for other kind of measurements as well. Okay, so let me minimize this one. So the first point is that I mentioned it somewhere along the video that PL over here represents photoluminescence measurements, that my photoluminescence measurements are saved in text files, as you can see over here. We have the first column corresponds to energy and the second column corresponds to intensity counts. So the first thing I need to do is to change this over here to .txt, because now I would be opening text files. Then I need to represent it. So let me find the other variables. We are talking about instead of. So now for the x-axis, I'm going to label it as energy, and its unit is going to be in milli electron volts. Similarly, instead of multiplying it with 3600, now we need to multiply it with 1000, convert it to millielectron volts. Similarly, for the units displayed on the figure, I don't want it to be in arc seconds, I want it to be in millielectron volts. So that's all the changes that you need to make for the photoluminescence measurements. Now let's run the program. And here are the photoluminescence measurements for the template. Open the file. And now you can see that my independent variable is energy. Sorry, this is not in millielectron volts. Let me update it. The x-axis is in electron volts. So the x-axis is in electron volts. Let us run the program once again. Full screen it. My independent variable is energy in electron volts, and my dependent variable is intensity in arbitrary units. This is a gallium nitride sample. Let me zoom in on the peak. And here the peak is approximately at 3.43 electron volts, which corresponds to the band gap of the gallium nitride material. We can zoom it out once again. Delete this data tip. It's in correct form over here. Okay, so that's how you perform the measurements in order to calculate the full width at half max and fractional full widths of the maximum peak for X-ray diffraction and also for photoluminescence measurements, and you can apply it to other kind of measurements as well. And that wraps up our tutorial on using MATLAB to calculate the full width at half maximum and fractional full width of the maximum peak, with a special focus on their significance in XRD, rocking curve measurements, and photoluminescence measurements. Whether you are dealing with symmetric or asymmetric curves or working with other techniques like photoluminescence, this tool will greatly enhance your data analysis efficiency. If you found this video tutorial helpful, don't forget to like, share, and subscribe for more tutorials. Feel free to leave any questions or comments below. We would love to hear how this tool is helping you with your research. Thanks for watching and happy analyzing with MATLAB. Take care. Adios.